In this section of chapter 5, I'll talk about aromatic compounds, its naming, and its stability on the basis of resonance. In earlier years, aromatic compounds were known to be those compounds which had flavor or aroma. These days, we have broadened that definition. Nowadays, any compound which is like benzene, so basically having single bond, double bond, single bond, double bond, or conjugated uh, multiple bonds, normally in ring structure. So basically benzene or its derivatives or compounds similar to benzene are called aromatic compounds. Now if you have a benzene ring, and there are two possible ways you can have two substitution groups. Let me draw one. This is the benzene ring, a double bond followed by a single bond, double bond followed by a single bond, and double bond. Now keep something in mind. In benzene ring, each corner has a carbon, and to satisfy four bonds around each carbon, you must have one hydrogen bonded to each carbon. So it'd be like this. So the formula is C6H6, even though normally we just write down a ring structure, but that's basically C6H6. That's benzene. So let me redraw it without the hydrogen so that you can better see the bonding. Now I'm going to write down 2Cl, and each Cl is like a substitution group. Remember I mentioned earlier that anything other than hydrogen, when it's bonded to a long chain or a ring structure, it is considered to be a substitution group. So if I have Cl here, would call it chlorobenzene. If I have Br there, call it bromobenzene. NO2 would call nitrobenzene. There is a table in this chapter. Make sure you know those names. Those are common compounds. Now if I have two substitution groups, I can place them in several different locations, in here, here, or here. You may think that what's wrong in placing a substitution group in this position I'm showing with another pen color, with this. Truly, this is a repetition of what I have already placed on the right hand side. If you draw yourself and try to name that compound, you'd find that they're becoming same as what I've shown on the right side. So if I'm using the first two positions of carbon on the benzene ring, I would have something like this. And this would be called ortho. So how would I name it? Orthodichlorobenzene. On the other hand, if these two substitution groups are in 1,3 position, so 1,2 position is ortho, 1,3 position is meta. This is called meta. I used to remember at your level by imagining some kind of tilted M in this case. This is M. That shows meta. Now I can also draw differently to show you meta. For example, this is my benzene ring. Now I have one chloro here, another chloro here. This is much better looking M. You can see this is M. That's how I used to remember it, so that I don't mix up with ortho and para. So that's meta. The other way of remembering it would be 1,3 position if you have groups. That's meta. Para is like this. This is my benzene ring. So I first got the benzene ring with double bond, double bond, and Cl, Cl, that's para. Again, I used to remember it at your level by imagining a P. So that's the P, P for para. So you can remember MOP, which tells you that how many ways you can organize the substitution groups, two substitution groups around the benzene ring. Meta, ortho, and para. Again, here you see ortho dichlorobenzene. I just mentioned about it. Again, you can imagine O passing through these. That's ortho. Now at the bottom, I wrote down different compounds, and I'm asking you to identify which one is ortho, which one is meta, and which one is para. Again, the first one is para. It's tilted P, or just remember 1,4. So 1,4 attachment. 1,4 means this is 1 and this is the fourth. No matter which way you start numbering, it's going to be 4. And this one is meta, second one is meta. This is 1,3 attachment. So this is the second one is meta dichlorobenzene, and third one has a common name. It's a meta attachment, but this is called metaxylene. So make sure you know these common names. It's on page 157, table 5.1. You need to learn all those common names. What would happen if you have more than 2 substitution groups? Like in this example, you can see 2 methyl group and a Br. Now here we apply what is called lowest possible sum, and then we apply alphabetic priority. We explained that lowest possible sum in the past, one of the slides in the past, but let's try to name this compound, and this is how we name it: 4-bromo 1,2-dimethyl benzene. So 4-bromo 1,2-dimethyl benzene. So if you want to write down the sum, it's with 4 plus 1 plus 2. That's 7. Now, if you want to number it differently, let's start numbering starting from Br. That's 1. The next one has to get 2. Next one 3. Next one 4. If that is the numbering, let's see what the numbers we have. For bromine is 1. Then first methyl group is 3. Second methyl group is 4. That's 8. So this is the only way you can get the smallest sum, the first one. That is 4-bromo 1,2-dimethyl benzene is the name of this compound. Now let's do one of the problems from the book, which is on page 159. This is the 7th edition of Fundamentals of Organic Chemistry by John McMurray. So on page 159, again, this is the question on ortho, meta, para, and you basically need to identify which one is ortho, which one is meta, and which one is para. So I'm just going to write down one of those. Now this will be fairly simple for you now. So let me write down question C. Remember I said that in aromatic compounds you have a double bond, single bond, double bond, single bond in ring structure, and would give you a specific definition of aromatic in terms of number of pi bonds, which is 4n plus 2, which we will talk about it towards the end of this presentation. SO3H and then OH. This is 5 point. This is this is actually 5.2. I think I mistakenly wrote down 5.2. This is 5.2C. So this is obviously ortho. You can see 1, 2 position. This is ortho. Now let's do 5.4, which I originally wanted to show you. So 5.4, draw the structure corresponding to the following IUPAC name. The first one is para-bromo-chlorobenzene. That's pretty straightforward. Para-bromo means one location you'd have bromo, and then you'd have chloro in its para position. So let's pick a different one, B. This is 5.4 B. Now this question is on para-bromotoluene. Para-bromotoluene. Now here you need to know what toluene is, and that's why I suggested that you need to know the common names of these compounds from the table. The first write down the toluene. Toluene has the benzene ring and a methyl substitution group. So rather than calling it methyl benzene, we call it toluene. So this is toluene. Now para-bromo, it automatically tells you that in para position you have Br. So that's how we get para-bromo. I ran out of space, but I'm hoping that you understand it. So this is para-bromotoluene. The last one, which is D, it says that draw structures for 1-chloro, then 3,5 dimethylbenzene. I always begin with the end part. So first write down the benzene, hexagonal ring, double bond, single bond, double bond, single bond, double bond. So that's how you get benzene. Now we know that they're a methyl group. And not only that, we know that there are two methyl groups. Di means two. So in position 3 and 5. So obviously your numbering starts with chloro, Cl, that gets 1. So let us start numbering. 1, let's use a different color of the pen. This is 1, this is 2, this is 3, 4, 5, and this is 6. So when you say 1-chloro, that's fine. 3,5-dimethyl. So this would be 3,5-dimethyl. This is the methyl group. 5 is another methyl group. Let's extend that a little bit so that you can clearly see it. So 1-chloro 3,5-dimethyl benzene. Even though benzene has double bonds, single bond, double bond, single bond, and double bond, so normally you'd think that it would behave like an alkene, having 3 alkene groups. But truly, benzene is unusually stable. It's not like an alkene. Let me give you an example of an alkene. This is an alkene, ethylene, and it can undergo reaction. We learned about Markovnikov's reaction, like for example HBr. H would go to one end. So if I change my pen color, say H comes over here and Br comes over here, the bond would be broken. So that's the typical addition reaction with an alkene. But if you add HBr to benzene ring, there'll be no reaction, which suggests stability of benzene ring. Now, this stability is due to resonance that happens within the benzene ring. Let me refresh your memory on resonance. Whenever there is an easy passage for electron or charges to go from one location to another, it is going to go. Keep in mind you're not allowed to move any atom. So let's see whether it's possible in here or not. If I move this double bond from here to here, at that point this carbon would have too many bonds. Don't forget that each of these carbon has a hydrogen atom. So this carbon temporarily would have 5 bonds, so it has to break its weakest bond, which is the pi bond, and then that moves to next carbon to preserve its 4 bond. Then same kind of problem happens to this carbon where I'm showing the hydrogen. Hydrogen is there. That would have 5 bond temporarily, so it has to get rid of its weakest bond, and it moves it to the next carbon-carbon location. So in other words, by doing all these movement of arrow, if you follow those, you end up with this. So basically benzene would give you 2 equivalent, we call these equivalent resonance structures. They look the same except the locations of the double bond. And actual structure will be explained by the combination of these 2 resonance structures. And often in the older books you'd see there is a benzene and followed by a ring structure. The ring is, circle in the middle. So that basically shows that it's the combination of these 2. That means double bond is not fixed. The second bond moves around the ring, and that's what is shown with this circle. In your book, they didn't really draw that circle. As I said, in the older version, I think two editions before this version, they used to show with circle in the middle. And many other books still show that. But your book shows individual resonance structures. Now, because of this stability, benzene doesn't undergo addition reaction like an alkene. But only type of reaction you can think about that can happen would be substitution reaction. That means one group comes in and substitutes hydrogen atom from the benzene ring. We'll discuss about those reactions in later slides. Now here we're showing you the difference between reaction of alkene and benzene. Potassium permanganate in presence of base. So this is a basic permanganate. I'm hoping that you remember the reaction. For basic permanganate, there would be syn addition of 2 OH groups. So this is the addition product when they add to these double bonds. So basically, we're showing you that how readily the double bond breaks down and attaches to 2 OH group. Similarly, HCl reacts according, and we discussed about Markovnikov's addition reaction, so we all already learned about it. However, if you're using the same chemicals to benzene, like potassium permanganate in water or in present base, nothing happens. There's no reaction. Similarly, when you add HCl to benzene, there is no reaction, suggesting that benzene is indeed more stable, a lot more stable than alkene. Now, oxidation reduction reaction, if I have a side chain like this, in this case this is toluene having an alkyl group as a substitution group attached to the benzene ring. If you add potassium permanganate, this is a neutral permanganate, then the CH3 becomes COOH. Now this is a very typical reaction, so that's why I have this shown in red. Any alkyl group with at least one carbon-hydrogen bond will undergo similar reaction, giving a carboxylic acid or COOH at the end. Let me show you what I mean by this. This is toluene or methylbenzene. If I have another substitution group instead of that, I'm writing down the way it's written down in your book, at least this edition of the book. Now instead of one carbon, let's assume that I have this carbon. This is isopropyl group attached to the benzene ring. Now this says, the rule says that any alkyl group, this is also alkyl group, at least one carbon hydrogen bond, that means which is attached to this ring. So 1, 2, 3, I have one carbon hydrogen bond. That means this is going to work. The permanganate is going to change it to benzoic acid or carboxylic group. On the other hand, if I have a T-butyl group, instead of having this, if I have a T-butyl group, let me draw one with T-butyl group. So this is a benzene ring, and let's write down T-butyl. 1, 2, 3, 4, all are carbon. And this carbon I'm showing with an asterisk. I think this bond is a little bit misplaced. Yeah, that's that carbon doesn't have any hydrogen. This is T-butyl group. This is T-butyl. T-butyl benzene doesn't react with potassium permanganate, so no reaction. So what we learned from here is the carbon which is directly attached to the benzene ring must have at least one hydrogen, and then and only then permanganate will change it to carboxylic acid. Otherwise, any alkyl group other than T-butyl would change that alkyl group to carboxylic group. As I mentioned before, reaction with hydrogen does not happen that easily. That's why you need to apply very high pressure. So then this double bond, single bond, double bond all becomes single bond, and they're all added to hydrogen. So basically in this structure you'd have 2 hydrogens per carbon, and in this case you have 1 hydrogen. You have 2 hydrogens here, and I believe that you all now know that carbon must have 4 bonds, so that's why they must have these hydrogens bonded. So that becomes basically methyl cyclohexane. Now this is fused ring structure, and it's called naphthalene. You probably heard about this name. And in presence of Br2, substitution reaction happens in this position. And these are aromatic compounds. Now this kind of rule is applied now, 4n plus 2 rule. Let's first apply that to benzene ring. This is benzene ring. How many pi electrons I have? Remember, this is not sigma, pi. So this is 2 coming from here, 2 from here, and 2 from here. So that's 6 pi electron. Now, does it follow 2n plus 2 rule? Yes. When n equals to 1, you have 4 plus 2 equals to 6. So 6 electron is valid, and so it works out for benzene, 4n plus 2. Now let's try it for naphthalene. Let's draw it a little differently, showing explicitly double bond or single bond. So let me draw that. Remember, it has a fused ring structure. So I have a double bond here, double bond here. So keep that in mind, that the double bonds are not next to each other. So there is a double bond followed by a single bond, then there's a double bond. That's how it works. That's naphthalene. Now, let's count the pi electrons. And I'm going to use a different colored pen so that you can follow. Only the double bond, the second bond, you need to count. This has 2, 4, 6, 8, 10. So in naphthalene there are 10 pi electrons. Now let's apply 4n plus 2 rule. n can only be integer, 1, 2, 3. If n equals to 2, for n equals to 2, we'd have 4 times 2 plus 2, and that's 10. And that works out pretty good. Naphthalene has 10 electrons, and 10 does indicate an aromatic compound, and it is an aromatic compound. So what are the properties of aromatic compound? Because of the resonance, they have high stability. They usually do not undergo addition reaction. However, they would undergo substitution reaction. And one such example is shown here, Br2 plus Fe, giving you Br substituted for hydrogen at this location.